Understanding the graphs of polynomials. So we're giving a graph and we want to describe some things about the polynomial. Here, this is a linear function. We know the degree of a linear function is 1. So it's going to have 0 turning points. You always subtract the number 1 from your degree to find out how many turning points it can have at most. So if this is degree 1, you subtract 1, you get 0, it's going to have no turning points. And we already know that about a line. Here we have a quadratic function, 2 quadratic functions. There's 1 turning point. And so we know that the degree has to be at least 2. And in fact, the degree is 2. Now, a quadratic function is going to have either 2 intercepts, x-intercepts, 1 x-intercept, or no x-intercepts. So this particular quadratic function has 2 x-intercepts right here. And this quadratic function has none. It doesn't even touch the x-axis. So, and then you could have another situation where you have a quadratic function that just touches it at one place. So the number of intercepts will not always tell you the degree. If you're looking and you see that this has no intercepts, you might think, well, is it a line? Well, obviously it's not a line because of the turning points. So it's the intercepts and the turning points together that tell you the degree of the polynomial. So we might say, well, this has no intercepts, so it could be linear, but because it has a turning point, we know it's not linear, it's a parabola. So you're going to use the x-intercepts and the turning points together to determine what the degree is. You can't definitively know the degree just from the graph all the time, but certainly you can for a parabola. You just look at that shape and you know right away that's a quadratic function, and so it has degree 2, and it can have 0, 2, or just 1 x-intercept. This quadratic function, we know the leading coefficient has to be positive because it opens up. And this quadratic function, we know the leading coefficient must be negative because it opens down. And looking here at this one has 2 turning points and 3 x-intercepts. So I know that it has to have at least degree 3. You're going to add 1 to the turning points. So we have 2 turning points. So we add 1 to 2, we get 3. We know that the function has to have at least a degree of 3. That's the minimum. Also, we have 3 intercepts, 1 right here, 1 here, and here. And so we know that the function has to have degree 3 at least. All right. Here, we only have 1 intercept. So you might say, well, this has to be at least degree 1, right? Because the degree matches the intercepts, but not always. We know that it has to be at least degree 1. But then when we look at the turning points, here's a turning point, here's a turning point, here's a turning point, and another, then we know, well, the x-intercept is not telling us much about the degree. The turning points, however, tell us that it has to have at least a degree of 5. That's the minimum degree because we have 4 turning points. And it makes sense because notice that the end behavior is going up in opposite directions. If the end behavior goes in opposite directions, then the degree has to be odd. And so that makes sense because we have 4 turning points, the degree is 5, and we can see from the end behavior that it's odd degree. Here, we can see from the end behavior that it's an even powered degree. And we can see that there are 1, 2, 3, 4, 5, 6 intercepts. And there are 1, 2, 3, 4, 5 turning points. You add 1 to 5, and that gives you 6. So the degree has to at least be 6. And you have 6 intercepts, so that tells you that the degree also has to be at least 6. We know that the leading coefficient here is negative because both open down. We also know that these two have negative leading coefficients because they go, the left is going up and the right is going down infinitely as far as the end behavior goes. So that's how we interpret the graphs of polynomials.